Good day, ladies and gentlemen. We are going to cover microstructures and mechanical properties of metals. We'll focus on these. We'll focus on the bonding, crystal structure, defects. And the reason why we are focusing on these is because they affect the properties of our structures. And the structure that we are going to look at are metals, ceramics, polymers, composites, and advanced materials. Under advanced materials, we have things like semiconductors, biomaterials, nanomaterials. I'm sure this is just revision. We have all covered this at one time in our lives. Atomic structure and interatomic bonding. The importance of atomic structure is because it affects the bonding. And an atom typically consists of nucleus and electrons, where the nucleus consists of protons and neutrons. And neutrons are electrical neutral, while the protons are positive and the electrons are negative. And the masses, protons and neutrons have same mass, while the mass of the electron is very small and it's usually neglected when calculating the atomic mass. The atomic mass is equal to the mass of protons plus neutrons, and isotopes arise from different number of neutrons. There are two types of bonding: your primary bonding and your secondary bonding. Your primary bonding has high bond energy, that's between 100 and 1000 kilojoules per mole. And your typical primary bonding is your ionic bonds, your covalent bonds, and your metallic bonds. And what is for the secondary bonds is the weak bonding, which is absorption energy less than 100 kilojoules per mole. And these are usually your dipole moments, your van der Waals forces or bonding. This table summarizes the effect of bonding on a property like melting temperature. You notice that metallic bonds, covalent bonds, and ionic bonds have high melting temperatures because of the nature of the bonding, while van der Waals forces or bonding and hydrogen bonding have low melting temperatures. Solids can be classified either as crystalline or amorphous. In crystalline materials, you see the order and the pattern in which atoms are arranged. But in amorphous material, there is no such order or pattern. Solids can be classified either as crystalline or amorphous. In crystalline materials, you see the order and the pattern in which atoms are arranged. But in amorphous material, there is no such order or pattern. Crystal structures. Why do atoms assemble into order structures? This is done to minimize potential energy. We have here particles which are far apart from each other, or atoms which are far apart from each other. As they come closer to each other, they release attractive energy, or they release heat, and then there is a decrease in potential energy. And as they come closer and closer, there comes a time when they start repelling each other. And this is the red part where they start repelling each other. And they require energy to be put together, and therefore potential energy increases. So the lowest state of energy, of potential energy, is this lowest point in the curve. And at this point, we have ordered structures. Therefore, energy of our crystal structures is less than the energy of our unorganized structures or amorphous solids. The properties of materials is directly related to the crystal structure. And the crystal material is the one which has atoms in a repeating or in a periodic array over a large atomic distance. And this atomic distance, or this large array, is composed of unit cells. So when describing crystal structures, it is often convenient to subdivide the structure into small repeating entities, which we have already said are called unit cells. And below is, or in the diagram, it's a typical unit cell. So now we'll look at this unit cell in one by one or in detail. The first unit cell that you're going to look at is called the first centered cubic crystal structure. The unit cell has cubes in each corner of the cube, and it has an atom in the middle of each face. Some of the materials that have such structures include copper, alumina, silica, and gold. The atoms touch each other, and we can have a relationship between the length of our cube and the radius of each atom. And this is represented by this equation. A is equal to 2r root 2. The derivation will be done during the tutorials. Two other important parameters for our unit cell are the coordination number and atomic packing factor. And the formula is given, and an example will be done during the tutorials. The next unit cell that you're going to look at is called body-centered cubic crystalline structure. In this case, we have atoms in the corners of our cube, and you have one atom in the middle of the cube. And you can relate the length of our cube to the radius of our atoms by this equation. A is equal to 4r divided by root 3. Obviously, in comparison to the previous unit cell, the body-centered cube structure has less atomic packing compared to the face-centered cubic structure. The next structure that you have is a hexagonal cross-peg structure, and there is a structure. And an important thing to note about this structure that it has similar packing with face-centered cubic structure. Another property of a unit cell that you can be able to compute is the theoretical density, which is calculated by this relationship. We'll wrap up this introduction on these definitions. Single crystal atoms in repeating or periodic array over entire extent of the material, and this is what is usually used for characterizing and determining atomic number and the structures of materials using single crystal microscopy. We have polycrystalline materials. These are materials composed of many crystal grains, and these grains can be oriented or have different orientations, and these are shown in the figure. You realize that these crystal grains are separated by boundaries, and their orientations are different. Other terms that you like to define are polymorphism and allotrophy. Polymorphism happens in metals and other nonmetals where this material has more than one crystal form, while allotropy is a case where an element can exist in different forms. For example, carbon can exist as diamond, as graphene, as carbon spheres. It can also exist as carbon nanotubes. Another characteristic that we have about our structure is that they have defects, and typically the defects are not a bad thing. These are sometimes required for different uses. For example, in the semiconductor industry, they require them, and also for diamonds, and there's the ones that give them color, and even in forging of materials, these are introduced to increase the strength of the metal. Also, even in catalysis, some reactions occur better or faster in the presence of defects, and defects are created or induced by thermomechanical processing. In this slide, we have two images, one of an ideal crystal and the other one of an actual crystal, where we start seeing quite a number of defects, and one of the defects that you're going to look at are called point defects, and the one shown in the fig is called a vacant or a vacant lattice. So in this case, we have an atom that is missing on our structure. So vacancy formation is driven by thermodynamics. So as vacancies are produced, there's an increase in entropy or randomness, which is usually the desired state for materials. And we can quantify the number of vacancies that can be created in a material under different conditions. And this is the equation that is required. These are the other vacancies that we have, or other point defects that you have. We have interstitial, we have interstitial impurity, we have substitutional impurities. Then we have what's called dislocations or linear defects. Some of the examples of these defects, we have edge dislocation, we have screw dislocation, and the details on these defects are there in our reference test. So the next thing is for us to do a tutorial on what we have covered. There are quite a number of calculations that you can do in what has been presented, and this will do in arrangement with our class reps.